All right, guys, welcome back. We're going to take a look at today at areas between curves. I just want to do a little bit of a reminder from your Calculus 1 course. If you have a function, let's call this function f, and let's say you're trying to find, there's two big problems in math. One of those is, can I find the area under a curve? I'm sorry, two big problems in calculus. One of them is, can you find the area under a curve? Exactly, under a curve, and let's say we're doing it from A to B. And if you remember in that course, what you did is you said, well, let me make a bunch of rectangles, right? And we made these rectangles and we add them up and we approximate it, right? So the area is approximately the height of the rectangle times the width, if you remember this. Well, the height is that functional value. Here's that height, f of x. If I call this that x value, height's the f of x value. The width we call delta x, the width of the triangle. All right, we had the width. So it's f of x times delta x. But we had to run a limiting process on this, if you recall, right? We ran a limiting process. So what we did was we said, well, let me sum up all these rectangles from I being 1 up to n amount of rectangles, but I'm going to let this be an infinite amount of rectangles. In other words, I'm going to make these rectangles, if you remember, we would make them, like at first we would make them this width, whoops. But the smaller we make the rectangles, the more exact it is, right? So if I run the number of rectangles to infinity, if I run that to infinity, in other words, the width of the rectangle is going to 0, right? Then that would give us the exact area of the curve, which is the integral from A to B. And that's a quick little overview if you remember that. So we have the integral from A to B, from A to B. The integral from A to B is the area of the curve, right? So what about the area between curves then for this section? Let me go to our notes for today. So here's two functions, f and g. If I was to draw the area under f, so this is the integral from A to B of f of x dx. Now remember, we want the area between, right? Between. So what if I look at the area from A to B of g? So the area under g. See how if I subtract that out, the area under g, see how we're left with the area in between? So let me put it all on the same graph here. Here's the area g. So if I subtract that out, I'm left with what I want there in yellow between them, right? So we're going to subtract the two, right? So area under f, subtract the area out, and I'm left with, all right, so here's, again, one more time, area under f, I subtract out this area, and I'm left with the area that I want, which is between them. So the area between and f is always the one on the top, and at least for this description here. That would be the area between the curves. All right, let's go ahead and look at this first example now. Let's find the area of the region bounded by the graph. So I'm going to go ahead and let me draw these two graphs. I've got x squared plus 2, so it looks like a parabola, but it's bumped up 2. Let me plot a few points. 1 squared plus 2 is 3. 2 squared, 4 plus 2 is 6. There's my f function, x squared plus 2. Let's go ahead and graph g of x. G of x is negative x. So I've got y equals mx plus b. I got slope of negative 1, down 1, right 1. Or you can plot points, however you want to do that. You've got a line here. There's my g function. And we're going from 0, from x being 0 to x being 1. Can you see your little area in red there? And so we're making our rectangles, vertical rectangles here, right? So I got to go f minus g. These are all my rectangles. Again, this is in red, but I'm just trying to show my rectangle. The height of it is f minus g. F of x minus g of x is the height of that rectangle. You with me? And so our area here would be from x being a to x being b of the top minus the bottom. Again, f of x luckily is the top. So we're going from x being 0 to x being 1 of f of x, x squared plus 2. There's my top one. And the bottom function minus the bottom function, which is negative x. And so we've got x squared plus x plus 2 dx from 0 to 2. And then we're going to go ahead and finish that. Oh, I'm sorry, 0 to 1. Thank you. Appreciate that. Zero to 1. Now we'll throw in the 1. Minus, now we got to throw in 0. That's a bunch of zeros right there. So it looks like I got a third plus a half plus 2. That's 2 6 plus 3 6 plus 12 6. This area ends up being 17 sixths units squared, of course, for our area, right? This would be a good you try it problem. If you want to pause the video and work through this problem, that'd be great. But go ahead and start graphing this thing. Notice my f of x here. I'm going to write it this way, negative x squared plus 2. So I've taken my parabola, flipped it around the x-axis, right? Reflection about the x-axis. And then I bumped it up 2. So negative x squared plus 2. Let's go ahead and graph g of x equals x. Here's our g function, here's our f function. And we want the area bounded by these graphs, right? So in between, right there in red, our rectangles here, vertical, so it's f top minus bottom are my rectangles, right? Top minus bottom, f minus g in this case. And then we're going from what x value to what x value. You can probably tell from my graph, since we did graph it already. It goes from negative 2, and notice they hit here at 1, right? If you didn't know, make sure you find their intersection first. Like, where do these two hit? Where does f of x equal g of x? Where do they hit? Well, where does 2 minus x squared equal x, right? F of x is 2 minus x squared. Where do they equal x? Well, this is a quadratic, so I got to get one side equal to 0. So subtract 2 and add x squared to both sides. You get x squared plus x minus 2. Go ahead and factor that. And notice they hit at -2 and 1. Just like we said, -2 and 1 is where those two intersect, right? So now when we set this up to find the area bounded by the two graphs, we're going to go from an x value of -2 to the next x value of 1, because remember, we're adding up all these rectangles, if you will, right? The height of the rectangle is f minus g. Here's my f of x minus my g of x, which is x. All right, here's my top, here's my bottom. So this becomes -x squared. Let me put the minus x next, plus 2 from -2 to 1. So this is -x cubed over 3 minus x squared over 2 plus 2x, -2 to 1. Put the 1 in. Minus, now I put the -2 in. Oh, I'm making a mess here. Oops. So that'd be minus, I'm going to take this through. Let's see, so that's that ends up being 9/2. So here's your setup. If you're checking yourself on this, you try a problem. Notice I graphed them, and we're doing the area bounded. So the area in red here. I had to find the intersection first. Where do they meet? They meet at -1 to an x value of 4, right? That's where they meet. So I got to go from -1 to 4. My lower and upper bounds on my integral. And then I'm going to go top minus bottom. Remember, we're making a rectangle. We're adding up all these rectangles, right? And the rectangle is the top graph, right? Top minus bottom. F of x minus g of x. In this case, this is your top, and this is your bottom. To make sure that your height is positive, I got to have top minus bottom, right? If I mix that up, it'll give me negative. All right, so let's go through here. And so I've got -x squared plus 3x plus 4 from -1 to 4. So I got -x cubed over 3 plus 3x squared over 2 plus 4x. And this is from -1 to 4. Let me come up here. And so I got -4 cubed over 3 plus 3 times 4 minus, now I got to throw in my -1. Sorry, I'm running out of room. Ugh. Let's see, 3 times 16, 48 over 2. So that'd be a minus, that'd be a negative times a -1/3. So it's a positive third. That's a 3/2. So -4. So all those are going to change. 20. Let me just write it out. Find those. 24, 64. Get a common denominator of 6. So I got -130 over 6. 264 over 6 minus 9 over 6. So your area ends up being 125 over 6. I think that's all simplified there. So let's look at this scenario. I've got the sine of x, I got the cosine of x. I want the area bounded, but I'm only on this interval from 0 to pi. So let's go ahead and graph just so you kind of remember. All right, sine of 0, 0. Sine of pi halves is 1. Sine of pi is 0. Sine of 3 pi halves is negative 1. Sine of 2 pi, 0. Let's get the look of the sine here. Now let's go ahead and graph cosine. So there's f, our sine function. Now let's do cosine. Cosine of 0 is 1. Cosine pi halves is 0. Cosine of pi is negative 1. Anyways, we graph this thing. You're like, oh yeah, I remember the old cosine, right? There's our g of x, which is our cosine function. Now we're only going from 0 to pi. So x being 0 is right there. Let me put a big black line. To x being pi is right there, right? X being 0 to x being pi. I'm bounded in there, but I want to find the area between the graphs, right? Do you see how they cross in between there? So initially, cosine's on top, right? The red one's on top, the cosine's on top, and then they switch, and then the sine goes on top until we hit pi, and then we're done, right? So what I'm going to have to do is I'm going to have to set this up twice, but first of all, where do they intersect? Where does the sine equal to cosine? Well, if you remember on the unit circle, right, I'm looking at the unit circle, they have the same, sine and cosine are the same, right? Where? Pi force, 45 degrees, right? At pi force, they meet, right? They also have the same, so here's at pi force, comma, whatever, right? They also meet again at down here. 3 pi force would be right. This is the next spot, but we don't get there. We stop at pi, right? So we don't care about the next one where they intersect. We just care about the pi fourth spot. So when we're setting this thing up, we're going to go, this area is from 0 to pi force. The red one's on top, cosine's on top, minus the sines on the bottom until we get to pi fourths. And then we're going to go from pi fourths up to, remember we're ending where? Pi, yeah, we're just bounded to pi. Okay. And now on that one, now the sine's on top, cosine's on the bottom. Okay, so this is our red area. This is the red one. Let's do the green over here up until pi. This is the green. So we got to add those two areas together, the red and the green. So we got the integral of the cosine is the sine. Integral of the sine is negative cosine. Integral of the sine is negative cosine minus integral of the cosine is sine. So we got sine pi force plus cosine pi force minus, now we're going to throw in 0. Sine 0 plus cosine 0. Now let me come over here plus, now I'm going to throw in negative cosine pi minus sine pi minus negative cosine pi force minus sine pi force. And so we've got sine of pi force, root 2 over 2, find the cosine of pi fourths, minus Sine of 0 is 0, cosine of 0 is 1. I got plus a minus, in other words, a minus, and then the cosine of pi is -1. Sine of pi is 0. And I got, you know what, let me just distribute that. So that'll be plus cosine of pi force and plus sine of pi force. Sine of pi force is √2/2. I distribute that there, so I got a -1 plus 1. So the -1 plus 1, those are gone. So it looks like I have √2 plus √2 plus √2 plus √2. That's 4 √2/2. So this area is 2 √2. Let's go ahead, pause it here, and start graphing and working on that next U-triad problem. Once I've got the graphs on these, and remember the e to the -x, that's going to reflect e to the x about the y-axis. Let's go ahead and find the intersection. Where do these things meet? Where does e and e to the x meet? We'll take two at a time here. Well, let's undo e with its inverse. Got to run the natural log. ln of e to the 1 is 1. ln of e to the x is x. So they hit at 1. There it is. 1, comma something. That's our first point where they meet. Let's do the other two. So where does e to the -x and y equals e hit? Set them equal to each other. Run the natural log. -1 is where these hit. So -1 comma whatever, right? Of course, it's -1e and 1 comma e. And so we're just finding, we're doing the rectangles top minus bottom, right? And it's all this area in there, top minus bottom. So our area would be the integral. If you notice, oops, before I grab, whoops, oh man. Notice I have top minus bottom. Here's top. The red one's bottom until when? What x value? From -1 until 0. Good. So here's these rectangles. So I got this black area, top minus bottom. So the top is e minus bottom, which is the red one, e to the -x. That's the black area. And then we got to go from 0 to 1, and that's the blue area. Top minus bottom is e minus the e to the x function. So here we've got the integral. Let me split this up. I got this, and then the reason I'm splitting this up is I got to use substitution right here. On this one, I do not. Oops. But the problem is this right there, right? I've got a composite function. So I'm going to have to let u be that -x. So the du is just a -1 dx. Well, the nice thing is I have -1 dx. There's my du. There's my du.
Did you need to get that from negative?
And so now we can just run this. And notice they're both, you've just got a constant on this, so you can actually put these two together. E plus e to the u du. And now we'll run it. And if you remember, the integral of a to the x dx is 1 over ln of a to the x, plus a constant. Of course, in this case, there's no plus constant. So that's what we're using here. But e is just a number, so that's just EX, right, plus 1 over ln of E, e to the u. Well, e to the u, remember, u is negative x. So let me put the u back in here. And then we're running this from -1 to 0. Now let's run this integral. Ex minus integral of e to the x, 1 over ln of e to the x, from 0 to 1. And I didn't give myself enough room here, so it looks like I'm going to have to come down here and kind of make a mess. So let's plug, sorry about that, plug the 0 in. ln of e is just a 1. Now let's plug the -1 in. Now let's go over here to this next one. Plug the 1 in. We got 1 over 1 here, e to the 1 minus, now let's throw the 0 in. So we got 0 plus, we've got the 1 over 1. All right, e to the 0 is 1. We got a plus, plus an e there. And then minus an e, because that's e to the 1, negative 1, e to the 1. I got that negative out front. Minus 0 plus e to the 0 is 1. And so it looks like e minus e, I guess that's gone. I got another e minus e over here, I guess that's gone. And so it just looks like I got a 1 plus 1. So this area actually just ends up being 2 on this. All right, let's go ahead and graph this next one. We got the square root of x, square root of 0, 0, 1, 1, square root of 4 is 2, and so on. So here's our square root function. Here's the y equals the square root of x. And then we've got this line y equals x minus 2. 0 comma negative 2, 1 comma negative 1, 2 comma 0, 3 comma 1, 4 comma 2, so on. Here's our y equals x minus 2. Now, but notice it says only the area of the region in the first quadrant that's bounded by square root of x, below by the y-axis, or I'm sorry, the x-axis. Here's the x-axis. In other words, the line y equals 0 is the x-axis, right? So y equals 0. And then our black line, y equals x minus 2. And it's only this area in the first quadrant. Can you see the area in the first quadrant in red there? Okay. Now, what I get a lot of the times is students will jump to, well, I'm going, and it looks like they, well, first they find the intersection. That's great. Find the intersection. Where does square root of x meet x minus 2? If you square both sides, make sure you check for extraneous solutions. Notice these don't hit at 1. They only hit right there at 4. Right? So again, when you square both sides, check for your extraneous solution. So that's where those two meet. Let's go ahead and find the area now. So be careful on this. You're bounded. You're making your rectangles here. You're bounded until that point right there at 2, 0. So you're going to cut this off. You're going to do this red piece first. Then you're going to do the blue piece after that. Okay, so the red piece would be top minus bottom from 0 to 2. The top is the square root of x minus the bottom, which is the x-axis, y equals 0 dx. Plus, now we'll do the blue piece. That'll be from 2 to 4. The top is still the square root of x minus, but the bottom now of the rectangle, right? Again, we're making rectangles on this. is that line x minus 2. And now we're running through this one. So this area will be, remember that's x to the 1/2. And over here I've got square root of x minus x plus 2 dx, 2 to 4. So we got x to the 1/2 plus 1, so we got 3/2 all over 3/2, in other words, times 2/3. Here I've got 4 to the 1/2 to the 3rd, so that's square root of 4 to the 3rd, so that's 2 to the 3rd, that's 8, and then 8 times the 2/3 is 16/3. Minus here I got 16 over 2, I got minus 8 plus 8. Let me distribute that. So that's a plus, negative times a negative, I got 2 square root of 4, that's a 2, minus a 4. So let's see, I got 8, negative 8, plus 8. So it looks like I got, oh, and it looks like 2/3 times 2 to the 3/2 minus 2/3, 2 to the 3/2 is gone. So this area ends up being 16/3 plus 2 minus 4. So we got 16/3 minus 2. So 16/3 minus 6/3, it looks like our area here ends up being 10/3. So we've done this one, right? We've done the top minus the bottom, right? We've done the vertical rectangles, if you will, sum them all up, right, with our integral. Now we're going to do right minus left in terms of y. So see how the rectangles are now, that's a very bad rectangle, horizontal, right? So like, for example, if you had like x being 5 and over here is like x being 2 and you're going from, I don't know, 1 up to 5 or something, right? 5 minus 1 gives you the height of the rectangle. That's a height of a rectangle 4, right? So right minus left will give you a positive rectangular height on these. So that's what you want to remember. So right minus left from y to y. So y being c to y being d, whatever c and d is, right? And you're summing up all these rectangles. That's what we're doing with the integration, right? We're summing all these things up. Doing that limiting process. So right minus left from y equals c to y equals d. So let's go back and actually do that same exact problem. Let me graph it real quick. So here's our graph, and what we're going to do is we're going to make rectangular rectangles here. Okay, so we got to have this, instead of y equals, we got to have it in terms of x. So instead of y being x minus 2, let me solve for x. X is y plus 2. Okay, so x is y plus 2. That's my right-hand side of this. Instead of y being the square root of x, let me square both sides. So x is y squared. Okay, x is y squared. Now I know it's only the top part of that parabola. X equals y squared, right? Because if you have y squared equals x, and you square root it, you'll actually have plus or minus root x. Here's positive root x. Here's negative root x. So x being y squared is that, right? But we only have the top half of this. Does that make sense? So when you're finding the intersection on these, if you set these equal to each other, where does y squared equal y plus 2, and you solved it? it would say at 2 and -1. Well, it doesn't hit at -1 because this doesn't have the other end of it, right? So we don't have that part. So forget about them hitting there. They only hit at a y value of 2. So here's, bless you. So here's our point. It was 4, 2, right? It was this y value, right, that they hit at. They meet square root of the x equals y squared and x equals y plus 2. Made myself a little room. So let's go ahead and find. Now remember, we're finding this area, right, in here. But of course, we're doing rectangles that are horizontal this time. So we're going to go from a y value of 0 to a y value of 2. Of the right hand, which is x equals y plus 2. So y plus 2, right side, minus, so here's my right, minus my left, which was x equals y squared, right? Remember, we solved for x there. So minus the y squared. And this is in terms of y dy. Okay? And that's all we have, instead of like before where we had to add up two different ones because we had to stop it at 2 because we have different top and bottom, right, situation. Well, we had the same top, but we had a different bottom on those. So this is a little cleaner for this one. So I got negative y squared plus y plus 2 dy from y being 0 to y being 2. Now we're going to go ahead and run it. So negative 8/3 plus 18/3. There's the old 10/3 that we had. This is not a bad problem, you guys, to pause and take a look at. But let's go ahead and graph, let's graph x minus y squared equals 0. So x would be y squared. And maybe just to make it easier on yourself, let me do it this way. Whoops. If I square root, I'd have the plus and the minus root x, right? So here's the positive root x, and here's the negative root x, right? That's what x being y squared looks like. We're going to do this with respect to y. So there's our parabola for x being y squared. That should be a little more curved right there, through there. All right, let's do this next one here. X plus 2y squared equals 3, or x equals 3 minus 2y squared. And maybe you want to just, you can plot some points if you want to take a look at that. If y is 1, for example, I got 3 minus 2 times 1 squared. If y is 0, actually I'll start with y being 0. Then I'll do it. If my y value is 1, I got a 1 here. How about if my y is negative 1? Well, negative 1 squared for the y is positive 1, so I got 3 minus 2 again, so I got 1, negative 1. Anyways, you could plot a few more points if you wanted to, but you're going to see this parabola like that. And they're obviously meeting right there. And where is there, and you could do that algebraically, where do they intersect? Where's their intersection? You have x equals y squared, you have x equals 3 minus 2y squared. Where does y squared equal 3 minus 2y squared? Let me add 2y squared to both sides. So I have 3y squared equals 3. Let me divide by 3. 3 over 3 is 1. Let me square root, so y is plus or minus 1. You see how they hit at this y value and that y value right there? And we're trying to find the region enclosed by these curves. And this is definitely easier to do with a right minus left situation. right? This is a very appropriate one for these horizontal rectangles. If I was doing it with vertical rectangles, I'd have to split it up. I'd have to go from 0 to 1. And now that's a real mess, right? Because I got the square root of x on the top, I got square root of negative x on the bottom, and then I got to solve this one for itself in terms of y over here. So I do here to here, right? Two separately. Again, that's a total mess. That's why we're going to do this horizontally. So we're making our cuts that way, right? And of course, this is the area that we're doing. So let's do the area. The area is right hand side. Well, the right hand side is that 3 minus 2y squared minus the left hand one, which is x equals y squared. Right? This is my left hand. This is my right hand. Red one. From a y value being the low y value to the high value where they hit. So our area is, and notice I have negative 2y squared minus another y squared, so 3 minus 3y squared. So this will be 3y minus 3y to the third over 3 from negative 1 to 1. Let me plug the 1 in. Minus, now let me throw the negative 1 in. All right, so here's our graph of this thing. Where do they intersect? Now, where does y cubed equal 3y minus 2? If you do it this way, if you see it on the graph, you can see they hit right here at that y value of 1. Of course, it's 1, 1. And they also hit over here at negative 8, negative 2, right? Those are the y values. If you do it algebraically, where does y cubed minus 3y plus 2 equals 0? And then you got to go back to your pre-calc. What are my possible zeros, which are factors of 2 over factors of 1? So plus minus 2 over 1, plus minus 1 over 1. Then you got to test them, right? Like which ones work. Negative 2, I'll jump to negative 2 does work. So now you're dividing 1 times negative 2, 0 minus 2, negative 4, 1. See how there's no remainder there. So negative 2 is a 0. In other words, y minus negative 2 is a factor of y cubed minus 3y plus 2. And there's the remainder, or there's that quotient there. So y squared minus 2y plus 1. So you got y plus 2, you got y minus 1. So these hit at a y value of negative 2 and a y value of 1, as we showed on the graph, right? Probably much easier just to do with the graph on this one. But anyways, that's where they hit algebraically. So where would the area be, the area bounded? So again, right minus left is a nice way to go on this. We've got these horizontal rectangles. We're going from a y value of negative 2 up to a y value of 1, negative 2 up to 1. And the right hand is the y cubed minus the left hand, which is that line 3y minus 2. And this is with respect to y. So we've got y cubed minus 3y minus 2 with respect to y, negative 2 to 1. Now we run it, y to the 4th over 4. Plug the 1 in. Plug the negative 2 in. Oops. Four minus 4 is gone. We have 1/4 minus 6/4. 5/4 plus 8. Well, 8 is 32/4. So it looks like this area ends up being 27/4. Thanks for watching. See you next time.